Good morning, everybody. Welcome to the third day of FOX. The first session today is on communication complexity, and the first talk is on compressing interactive communication under product distributions by Sasha Schuster.
Thank you. Is the sound okay? Perfect. Consider the usual setup for communication complexity. We have two communicating parties. Each of them receives an input, X for Alice and Y for Bob. Moreover, each of them has access to a private source of random bits. So once they receive their inputs, they proceed to carry out a conversation between them. Depending on those inputs, we let pi denote the transcript of that conversation. So in this setup, X and Y are some random variables that are correlated in some fashion, perhaps very complicated correlation between them. And pi is the third random variable that depends on these two. The following definition was made a few years ago in the groundbreaking work of Barak, Braverman, Chen, and Rao. It captures the information content of a communication protocol. And the notion is as follows. The information cost of a protocol is the information that the participants learn about each other's inputs by participating in the protocol. Formally, it's the mutual information between the transcript and Alice's input conditioned on Bob's input. So the first term captures the information that Bob learns about Alice's input from the transcript of the protocol. And the second term, symmetrically, quantifies the information that Alice learns about Bob's input from the transcript of the protocol. I should mention that this definition was preceded by several earlier ones, but this is the de facto standard notion of information cost. A fundamental problem that has been on the agenda for quite some time now is whether every protocol can be compressed to its information content I. Now, a very important special case of this problem was solved decades ago by Shannon in his breakthrough work, in his seminal work on information theory, where he showed that the restriction of this problem to one-way communication does have an efficient solution. It is always possible for a sender to transmit a message to a receiver using, in the limit, no more than the entropy of the message bits. So every message can be compressed to its information content in the limit if we consider one-way communication. The extension of this question to arbitrary communication, so two-way communication with no limit on the number of alternations or rounds, is wide open. More formally, what do we mean by compressing a protocol? By that we mean conceiving of some alternate protocol pi prime that is hopefully much shorter. We are free to use shared randomness. In fact, without shared randomness, this problem is completely hopeless. And the guarantees that we're looking for is, once again, that the transcript be very short, ideally comparable on the order of I, where I is the information content of the protocol. And secondly, it should allow us to simulate the original protocol accurately. So when you consider the tuple X and Y, then some decoding of the new protocol transcript that may depend on Alice's input, and some decoding of the new protocol transcript that may depend on Bob's input, that tuple should be close in statistical distance to the tuple X, Y, pi, pi. Okay, so the parties should be able to engage in this new protocol, which is highly economical, communicates very few bits, and yet allows both parties to conclude from the communication that they've engaged in, to infer from that communication a particular transcript of the old protocol and the distribution should be basically indistinguishable. So, as I mentioned, this problem has attracted the attention of the community for quite a few years now. Unfortunately, in the general case, in the false generality, the results that are known can be summarized on one slide. The first line in this table is a compression scheme due to Barak, Braverman, Chen, and Rao that compresses any protocol with communication cost C and information cost I to a protocol with communication square root of IC. So basic properties of the entropy function ensure that C is always at least as large as I. So this is a strict improvement on the original protocol. But unfortunately, C can be basically infinite. In fact, in many applications, in many situations involving information complexity, C is extremely large. It's at least exponentially larger than I. So we definitely are looking to obtain stronger results than this. An incomparable result was obtained by Braverman, who showed that any protocol with information cost I can be compressed to 2 to the I bits of communication. So here there's absolutely no dependence on C, but the dependence on I is arguably quite large. For several years, it was open whether this was in the nature of things or whether, in fact, the exponential barrier could be overcome. Well, those hopes were dashed a few years ago by the breakthrough paper of Gilad, Cole, and Raz, which shows that there are indeed communication problems where you cannot compress the communication to less than 2 to the I, where I is the information content of the protocol. Now, this is for general distributions. A well-studied special case of the problem concerns product distributions. So in this special setting, we're interested in Alice and Bob's inputs being independent random variables. Since the general case leaves us no hope for an efficient solution, it's natural to consider a special case like this. For example, the canonical special case where Alice and Bob's inputs are independent random variables. And here, the results, the table looks dramatically different. First of all, BBCR are able to improve their compression scheme to I times polylog C bits of communication. And of course, Braverman result still applies. Fortunately, the exponential lower bound no longer applies in this setting. And this leaves some hope for obtaining an efficient compression scheme for product distributions at least. And indeed, such a scheme was obtained a few months ago, was presented at STOCK this summer, which is able to compress the communication to I squared bits, roughly. So if you think of the top two lines, it really achieves the best of both worlds, because the top line has a mild dependence on I, but unfortunately it depends on C, whereas the second line has no dependence on C, but a very bad dependence on I. This result by Cole, very surprising, achieves the best of both of these worlds. You could ask whether this compression is optimal, and indeed this was one of the open problems in that paper, and we're able to solve it in this work. So the main contribution of this talk is to show that in the canonical case where Alice and Bob's inputs are independent random variables, it is possible to compress the communication essentially all the way down to its information content. And of course, you cannot do better than I. So this is basically optimal. So here's the formal statement of our main result. Let pi be any public or private coin protocol. Let mu be any product distribution on the inputs. And let I be the information cost of the protocol under mu. Our main result says that for any error parameter epsilon, there is a public COIN protocol that simulates the original protocol under mu with worst case communication cost I over epsilon. So this communication upper bound is optimal up to a logarithmic factor. Okay, in what follows, I will sketch the proof. Let me start with some background on protocol compression. First of all, in this talk, we will draw all trees upside down, or maybe as they should be drawn, because the root should be at the bottom after all. A cut in a tree is any set of vertices that intersects every root to leaf path in exactly one vertex. Okay, so the leaves definitely form a cut. Another cut in the tree is the root. That's another cut. But there are many non-trivial cuts. For example, here's one and here's another. When you take two cuts and consider their floor or their ceiling, those are cuts as well. So that's the ceiling of two cuts, and that's the floor. To remind you, we're working with the probability space where x and y are independent random variables, and pi is a third random variable, which is the protocol transcript. It depends on the first two. We'll let p denote the marginal distribution of the transcript. And as usual, we'll have notation for the conditional distributions. So for given inputs x and y, p sub xy is the conditional distribution of the protocol transcript conditioned on the inputs being x and y. And we likewise have distributions p sub x and p sub y. These are functions defined on the leaves of the tree. But you can also extend them, as we will have to all leaves of the tree, to all vertices of the tree additively. So these functions extend to internal vertices by defining them at a given vertex v as the probability of reaching a vertex in a subtree rooted at v. So the standard extension. Okay, in this terminology, the protocol compression problem can be presented as the following sampling challenge. The goal on input xy is to sample a leaf v according to the distribution p sub xy with communication ov. Now, unfortunately, neither party knows p sub xy. Right? The distribution that they both know is p. Fortunately, that commonly known distribution is already quite close to p sub xy on the average. So by the definition of information cost, we have the following identity. On average, for a typical input xy, the Kullback-Leibler divergence between p sub xy and p is small, is relatively small. So the problem is well posed to start with. We also need to take a local view of divergence and not just the global view of divergence at the top level. When you isolate a particular vertex v and ask how p sub xy diverges from p, you find that that quantity is the sum of two simpler quantities that the two players can compute in isolation. So this will be critical to the analysis. And this top quantity we'll call the divergence at v, and these bottom quantities are the corresponding divergences due to Alice and Bob. So they measure how the local probability at that particular vertex differs from the true probability. The chain rule ensures that when you sample a typical vertex of the tree and add up those divergences on the path from the root to the sampled leaf, on the average, that is going to be a small quantity. In particular, when you're sampling according to p sub xy, the typical sum of the divergences will be at most will be exactly, in fact, the Kullback-Leibler divergence between p and P sub xy. So when you consider the average situation, then both terms have to be small. Both have to be roughly I. And the final definition that we're going to look at is that of a frontier. Was introduced by BBCR. So here we'll look at the set of all vertices such that the sum of the divergences on the root to leaf, on the path from the root to that vertex is at most delta. In our application, delta will have to be 1 over log I. So as you would intuitively expect, when you consider the vertices up to the frontier, the probability distributions don't have enough time to diverge. In particular, in this blue region, the probability distribution P sub x is roughly the same as P. An analogous identity holds for P sub y in Alice's region. So now we have enough terminology introduced to state the previous algorithm and our new algorithm. So this is the original algorithm of BBCR. What the parties do is try to sample a vertex on this sampling cut, which is shown as this purple line. For this, they sample a leaf according to the commonly known distribution P and compute the intersection of that path with the purple cut. So right away, you know that the vertex on the purple cut is distributed according to P. Now, by the properties of the purple region, you know that P in that region is almost the same pointwise as P sub xy. So we're home free, essentially. What we need to do is correct the probability ever so slightly using rejection sampling. This is it. It's an extremely elegant algorithm. And the correctness proof is essentially 2 lines. The probability of accepting in the rejection sampling step is a 4th, and conditioned on acceptance, you have that the probability of selecting a vertex is exactly the true probability. Unfortunately, the cost is quite high because computing the intersection of the path with a purple cut could be very expensive. It could incur a cost of log C. Cole improves on this situation by discretizing the tree. So she replaces the frontiers by their rounded versions. The discretization works as follows. We consider the set R sub theta, which is the set of all vertices such that the frontier, Alice's frontier, is encountered in for at least theta fraction of the inputs on the path from the root to that vertex. And for different values of theta, you have this nested family of contours. Likewise for Bob. And what Cole does is literally round the frontiers up to this predetermined, commonly known small family of cuts. Okay? So literally, the frontiers f sub x and y sub x become replaced by f sub x bar and f sub y bar. And now computing the intersection of the sampled root to leaf path with the sampling cut is extremely efficient. It only requires a logarithmic number of communication. Now the actual protocol is slightly more subtle because once you cross the frontier, as you do in this region, only one of the parties can do the rejection sampling. And likewise, that region requires Alice to be in charge of the rejection sampling. But nevertheless, the protocol, the same idea roughly, allows you to conclude that the protocol works. So this is the calculation that shows you that the probabilities work out correctly. Now, the inefficiency in this protocol is is due to two reasons, due to two facts. First of all, when the parties sample a path, the portion of the path below, or rather above the sampling cut gets discarded, which is unfortunate because that segment contributes to the communication cost. But nevertheless, it gets discarded. Another source of inefficiency, which is even more important, is that whenever a path gets sampled and unfortunately ends up in the wrong region, so in the follower's region as opposed to the leader's region, then that path gets discarded entirely. Not any segment of it gets retained. In general, the communication cost of a step is proportional to the sum of divergences on the segment that you do retain of that path. So the more of the path you discard, the more effort you've wasted. When you look at the calculations in this algorithm, you find that a single step of the algorithm incurs I bits of communication while making roughly less than a constant bits of communication, bits of information in terms of progress. So that gives you the quadratic complexity. What we do is we eliminate both sources of the inefficiency. In the first case, we sample according to a more complicated hybrid distribution where the follower combines both the distribution that is of interest, so P sub x, and then the final segment, which is of no consequence, gets sampled according to the commonly known distribution. And the second more important change is we truncate the tree effectively at the intersection of these randomized frontiers, R sub a half for Bob and R sub a half for Alice. This has the effect that with constant probability, any path sampled by Alice or Bob gets retained over the choice of the other party's input. So the highlights of the analysis are as follows. Now the progress in our algorithm is exactly proportional to the cost. Specifically, it's a constant plus the communication cost. And the challenge is to show that the progress is non-trivial. So it's the exact opposite situation from BBCR and Cole, where it was trivial to show that the progress is non-trivial. And the difficulty was that the progress was not proportional to cost. In fact, it was disproportionately higher. So in our case, this is the main technical challenge of the paper. It's about realizing that for any fixed vertex of this truncated tree and random inputs, at least one of the frontiers is encountered on the path from the root to V with good probability. But unfortunately, the sampled vertex is neither fixed nor independent of x and y. So there may be all kinds of weird correlations that may defeat the progress measure. So what we show is that correlations, if any, must in fact contribute to the progress measure as opposed to defeating it. So the two open problems, the two main open problems in this area, they're widely known. First of all, can every protocol with communication cost C and information cost I be compressed at least approximately to its information content? So we know that the polylogarithmic dependence on C is unavoidable, but can this even be achieved? And lastly, it would be of interest to obtain a stronger separation of information and communication. The best known separation due to Gilad, Cole, and Raz is a separation roughly of the form log n bits of information versus log n bits of communication for a function on n bit inputs. So getting a separation of n versus log n would be ideal. Thanks.
We are running behind on time, so we'll have just one quick question, and while the other speaker sets up.
Can you repeat the question? It's hard to say. So certainly the general problem, the crux of the problem is dealing with these correlations, which defeat the analysis. So some tools may indeed carry over, but the fact that the inputs are independent is crucially used in the analysis. So as is, the proof certainly cannot be ported directly, but there's some hope that the techniques may be useful. Yeah. Thanks.
Okay, go ahead for pre-position.
Oh, that is a well-studied dimension of the problem. If you consider protocols with a fixed number of rounds, then we know how to compress the communication optimally. So there's a result by Braverman and Rao that achieves just that. The difficulty is when the alternations are exponentially in number.
Let's thank Sasha again.